Howdy, folks. Hope you're doing well. I'm hoping that Module 1 went by pretty easily, that you were able to get everything downloaded, installed, and understood, at least enough to where we can go into Module 2. And in this module, I'm going to answer the big question. What does it all mean? We're going to go through what we're going to call numerical or quantitative variables and look into measures that deal with these variables, including the mean, as well as things like the variation, standard deviation, and all that kind of stuff. And so, yeah, with that, we're going to use some graphs. I'm going to show you how to do all these things with Jamovi as well. But sit back, take care, and let's get started. All right. Now, given all these things, we can go through and look into Module 2. In this PowerPoint presentation, we're going to explore univariate descriptive statistics and discuss our measures of central tendency, as well as our measures of dispersion. And we're also going to look at some graphical measures as well. These descriptive statistics, as we'll come to learn, are only really appropriate tools for summarizing data when the variable is continuous or a numerical variable. Continuous variables are typically types of numeric variables that we'll use. We're going to go ahead and we're going to aim the goal to making numerical data count. I think we can do it. We're to talk about some descriptive statistics of numerical data, including measures of center, and the mean, the median, the mode. We'll also go into measures of dispersion, which involve the minimum, the maximum, and the 5-number summary, as well as standard deviation. And we'll lead into graphical representations using graphs through what we call histogram density plots, as well as box plots. And we'll also look into some certain properties, the shape and the skew of these graphical representations, maybe even see a special one here or there. All right, let's begin. With the descriptive statistics, we want to summarize data so the data is understandable by performing a function of data reduction. And what data reduction really just means is that instead of having 14,000, 50,000, 2 million different observations, we're going to summarize these things with a set of numbers that gives anybody who's reading these things a good picture and understanding of the data without having to look through the lines and lines and lines of code that would make anybody rip their hair out. We also have univariate statistics that we're going to analyze. Uni meaning one, variate, one variable statistics on the numeric data. So survey questions where the response results in an actual number report. And remember, this is a number that we can do mathematical operations on. So something like zip code, while it's usually comprised of numbers in the US, doesn't necessarily mean it's going to be the same thing for taking averages. It doesn't make sense to take an average zip code of saying 41164, 40475, take the average of the two. No, we may see how many people are in each of these area codes or in these zip codes. My bad. But it's not something that an average makes sense with. Some examples, since there's not a lot of continuous or numeric variables in the general social survey. So things like age makes sense. Respondents' education level, so how many years of formal schooling do you have? Now this is where it gets interesting. Educational level can also be done as qualitative if we think about it in terms of high school, college, maybe less than high school or something. But if you ask for how many years of formal schooling do you have, that can be derived into a numerical or a quantitative measure. You can also look at family income. What's your family's income? And usually with inflation, that's what like con inc is. or respondents' television habits. On average, how much TV do you actually watch on a given day? When exploring the numerical variables and their data, we're typically going to discuss properties of what's known as a distribution or a pattern of a variable. Basically, based on all the values that could be, which values come up and how often. And that gives us a specific pattern of the data. When I think about statistics and data, it's going to say of how things are distributed among all the people that we collected information from. And they usually get focused in terms of our summaries of certain properties like the center of our data, the spread or variability of our data, the shape of our graph, as well as the outliers or unusual observations that sort of differentiate from what we really think the data is supposed to look like. And we'll explore each of those things here in this module. The measures of central tendency are often thought of as measures of sort of typicalness, what we expect it to be. They provide one number reports on the distribution's middle or center point, the center, what it tends to go to. And the three main measures of center are the mean, the median, and the mode. For many of you all, you've seen this in maybe high school, middle school, maybe even elementary school. Or you may have seen it in another college class. These three are pretty well known, and if not, we're going to go over it. Quick and easy and get it done. Now you're going to start seeing formulas. I'm going to tell you right now. Don't get boggled down by them. This is my reminder to you all. We're not going to be doing any computations by hand. I feel it as a statistician that I have to do some formulas in there for those who can see it. We're going to focus more on interpreting the numbers that come out of it. And the numbers that come out of it are ones that Jamovi is going to do the dirty work with. So you all don't have to do that difficult stuff. You just have to be able to interpret what's going on. So the definition of a mean is basically the average of how people responded to a particular numeric survey question. And while you see these really strange formulas, this mean, this big sigma thing is known as a sum, adding them all up. This x little I or x sub I is the numerical value for each individual in the variable. So if I were to have x sub 3, it would be that variable for the third person in our survey. So if I go to the general social survey, person number 3 would have a response that would be equal to what our x3 is, and go all the way down to x 12,000 if we needed to. And then n, in this case, would be a capital. I have it as a capital N because that's what Jamovi will use. But also you can think of it sometimes as a little n for survey. So if you see a little n or a big N, the total number of people who responded to the question, or basically the size of our group. Now, many folks, instead of saying just mean out, I'm fine with the word in this class. I don't find it too big of a deal. But if you want to use the specific fancy stuff for statsy nickel and dime terms, many folks will use symbols for the mean, like the word or the letter mu. It's the Greek letter mu for population mean, and x bar for the mean of our survey or a sample. That's basically the smaller group within our population. So for this class, we'll just write mean. That'll be fine. But there are other ways you may see it out into the real world. The official middle of the distribution is known as our median. It's where half the respondents have reported being under that value and the other half were above. The median, or if I call it MDN for short, that's fine. We basically, to find it, we just got to take all the values in an array, basically all the numbers going from low to high, so all the values in that variable, and put them in order. If the number of observations is odd, it's going to be the exact middle number. If it's even, it's a little trickier. Actually, what you'd have to do is you take the average of the two middle observations. So you take the two middle numbers and you take the average of them. If you want to get very fancy in a population median, you call it something eta. But for sample medians, which you may see often, we use the capital M. But if in this class, if you write MDN or median, that's fine by me. I'm not worried too much about that. But make sure that you're using something like median or mean or MDN, or eventually when we go to the next one, which is mode. But try not to use too short of shorthand. If I see a capital M there, I'm going to think of it as the median. The mode, I think the easiest thing to remember about the mode is the most. It's the most often reported score or value of a distribution. So the formula for a mode, basically you take the score that appears the most. If no value appears more than once, so they're all equally the same value, everybody has a different value, we don't consider there to be a mode. It just thinks it. We think it's going to be something that's called uniform, where it's all the same. But you could have one mode, or you could have two modes if there's two different numbers that are happening the most, or three modes, or 17 modes. It doesn't matter if we have more than one. We just got to have something that, some observation, some value that is happening less than the others for a mode to exist. All right. Hope you feel good. Take a short break. We're going to go ahead and give you, I'm going to skim through the quiz stuff and let you take that, try that, pause the video, make sure the material makes sense, and we'll get going to the next piece. Into measures of dispersion. Now, this is going to be a busy one, so be ready. Have the time, take the breather. We're going to go through a lot of stuff, but you got this. There's more to data than just the measure of center. You could have two sets of data with the same means, same medians, and the same modes, but very different patterns. So for example, if I were to go ahead and take something that looks like a single data set that has a mean, median, mode of 0, one could be going from, or not 0, mean, median, mode of 10. My apologies. You could have it ranging from 0 to 100 for one of the data sets, and the other one could be from 5 to 20, and another one could going from 9 to 11. And those are very different groups. One ranges a lot, one ranges very little, and one ranges just right, but they all could have the same mean, median, mode. So we want to know how, not only what the centers are, but how the data seems to be dispersing. And we can do it through certain measures of dispersion. These are descriptive univariate statistics that might be used to take our numerical data and summarize the spread or the variability of the distribution. We'll start with the minimum and maximum, then go into something called the standard deviation, and finish up with something called quartiles and the 5-number summary, which sounds like a really bad band that's just starting up. The quartile, we're the quartiles and the 5-number summary. But really, it's a way to summarize our data and our statistics they go through. Now, reporting the tail ends, that's basically the beginnings of a minimum and maximum. It's basically saying, what is the lowest value we're getting? What's the largest value we're getting? To find them, once we put that stuff in order, just like we did with the median, you just gotta have the smallest and the highest value. The lowest reported value is blank, and the highest reported value is blank. We may want to avoid saying minimum and maximum. It's often used as sort of a jargon, and so I won't criticize too much, but be careful. When reporting your results, try to think of how things might be varying from one area to another, from one value to another. So is say ranging from these values or so on, that makes a little bit more sense. And it sounds less like I'm talking to a robot. So we're going to vote, so avoiding the minimum, maximum, maybe using things that are synonyms to it or similar sounding. We'll go through some of that stuff with the rules of writing to get you comfortable as well. So how do we summarize these tail ends? So something where I have these descriptives and I just have the minimum and the maximum. Well, looks the minimum 0 and the maximum 24 for the number of television hours daily. Well, it means the lowest reported number of hours were 0 hours of TV watch, and the highest number of reported hours was having the television on all day and all night long, 24 hours being reported. It makes me think of apparently there is this woman in the 80s who decided that she was going to make sure that, television history wasn't going to be lost. And she ended up recording years of television on her TV, whatever was playing. She just played it 24 hours and it has this like digital, well, I guess more film library of just everything that was on television for like over a decade. And so she would be the person that had the TV on all night long for 24 hours. Well, other folks who are chilling, not watching TV might report 0. And really, how do we write it? Just write it like that. It's a lot of these things should say, we're reporting the minimum and maximum. If we say these things that are a little bit less formal, there were people, for example, in the blue, there were people who reported not watching any TV per day, minimum equals 0, while there were others who reported watching TV for an entire 24 hours each day, max 24. By reporting the minimum and maximum like that, in parentheses, as a side note, we're reporting a fuller picture while not necessarily making it feel like we're talking in too formal of a tone. There's a level of formalness I think you all have the capacity to do. Many of you all are working full time. You're in this formal setting. This is a way to take the way we talk about these things, just like we talk about something else in sociology, but then taking that and turning the number part into parentheses. So if someone wanted to check it in a very cold numerical form, they would be able to see that summary really easily. Now, the minimum maximum are good first steps. We also love to figure out a way to discuss how varied or spread out the data is. We don't know what the data could be even when we have the minimum and maximum. So another measure of spread is the standard deviation. All right, deep breath, you all. It's going to be okay. The standard deviation formula is taken by taking whatever we think of as basically the squared differences an observation is from the mean, or that is the squared deviations from the mean. Standard deviation is related to the mean. So we basically want to say, what is some measure to see how far away observations are? And they said, all right, you could square it. If we square it, then we'll go ahead and we'll add them all together, divide that by n minus 1. And then since we squared a bunch of stuff, we're going to reverse it by taking the square root. And it's kind of like a distance formula, so to speak. I don't want to call it too much like that, but it's like an average distance formula, which already I'm sure some of you all are like, ah. The symbol looks gross. The S, well, it does have the same thing as Superman. The real Superman in this case is Jamovi. This stuff looks gross. It's not fun. It's not fun to do it by hand by any measure. But don't worry. For our purposes, we don't have to calculate the standard deviation by hand. Instead, we'll focus on Jamovi and do the number crunching for us. Jamovi fits the bill. Okay, Professor Sparks. But what does the formula actually mean? I get that you're showing me these things. It's fine. But give me what it's really supposed to be about. Here you go. The standard deviation basically says the average distance that most people's responses fall from the mean of all the responses. how far those observations differ on average from the mean itself. Now, reporting the standard deviation, remember it's not a standalone statistic. It must be reported with the mean to make any sense. And that the standard deviation measures the spread about the mean, it should only really be used when the mean is the most appropriate measure of center. Now, using the mean and the standard deviation to describe our respondents, actually, it's kind of neat. I think it's neat. You all might disagree with me. It's fine. I get it. I have unique mathematical interests. If some of you all can be down with it, I'll take it. But the cool part is actually, if I were to take my mean and take my standard deviation, takes two standard deviations above, two standard deviations below, at least 3/4 of all respondents are going to be between those two standard deviations from the mean, no matter what. Math has proven that at least 3/4 will be within that range. If the shape of the data actually looks like a bell, and we'll get back to shapes and bells soon, we'll come back to it in a couple slides going forward, we actually get an improvement from at least 75. We said about 95% of the data is going to be within two standard deviations from this mean. We can also look at a spread of numerical variables looking at percentiles. Percentiles, some of y'all, when you're dealing with standardized testing, you know what this stuff is about. If you were to fall in the p percentile data, that means your response is higher than p% of all the observations recorded. Now, we'll look at some other ones, percentile, sometimes every 10% people do. We often focus on the 25th, the 50th, and the 75th percentiles in our data, known as our quartiles. So breaking the data into quarters. And the 50th percentile is just another way to describe something we already just did, which is the median. If we break our data into lower halves and upper halves, the median of our lower half is then our 25th percentile. And then the middle of our upper half is going to be our upper quartile. Now, instead of saying lower quartile, we might say the first quartile, which is where Q1 comes from. Likewise, along with upper quartile, we might call it as the third quartile or Q3. Quarters, 3/4 is 75 cents, so the upper quartile is then Q3 or the 75th percentile. The 5-number summary of a data set could also be used. We could take those quartiles, Q1, Q2, Q3, or Q1, median, Q3, and include the minimum, the maximum. And when you do that, you go and you break the data into 4 quarters. Each of these ranges going from the minimum, Q1 is 25% of the data. Q1 to Q2, or the median, is 25% of the data. Median to Q3 is another quarter, and the Q3 to the maximum is our largest quarter or our highest quarter. And this also gives us information about the variation in all 4 quarters of the data. And Jamovi will do this as well. Mind you, I'm talking about this stuff. You use this process just like you'd use a computer, and now it's be able to interpret what's going on. Now, based on the Jamovi output for the variable TV hours, what would the 5-number summary of our data be? I'll take a pause, let you pause the video if you need to check it and see if you can get it on your own. If not, we're going to keep going. Go to the next slide, and I can go ahead and see that right here, based on what I use from Jamovi, it'll put the minimum and maximum and the 3 quartiles right all next to each other. And also note the median is included. It's also the same thing as the 50th percentile. And it shouldn't be different. If you ever saw something that was different, there's something going wrong. And we need to check it and make sure and fix things if needed. But the minimum here was 0. Q1, the 25th percentile, is 1. The median, which is 2. The third quartile, which is 4. And the maximum, which was 24. Not too shabby. Well, now we're going to switch gears, go from making numerical summaries to graphical summaries. Because I'm sure you all have heard the old saying, a picture is worth 1,000 words. Data does the same thing. In statistics, we turn numerical summaries into visual representations or pictures through what we know as graphs. And a graph, an effective one at least, lets the data tell the story. It includes appropriate labels and titles to describe what's going on and uses the amount of ink that's proportionate to the information involved. So we try to avoid chart junk. We'll see some examples where there is some we might want to avoid and get rid of. So if you go to the Jamovi tutorial, you'll see what I mean. Now, the graph gives us a good understanding of where values seem to be falling. It helps give patterns and all sorts of nice, neat things, including the shape. The shape for numerical data is one of the most important features of the distribution of a data. Things like a bell-shaped, or something that's triangular, or uniform or rectangular, or there's a J shape, reverse J shape, something that's very right skewed, left skewed, bimodal, 2 modes, or multimodal, 3 modes, because it's multiple. And there's different ways to talk about how the graph is shaped, which also describes how the pattern of data seems to be distributed. It also leads into another property which is known as skewedness. Skewedness is a property of the distribution that describes how evenly balanced the data is over its spread. We'll look at something that's called its tail, basically where the data seems to peter off. Where there's little data, shrinks as we go. And visually, it's not too hard to find out what kind of skewedness it is. The distribution is skewed to the right if the tail goes to the right side of the data. So right here is an example. It's skewed to the left, as you see here, as well as the J-shaped distribution, if we have a tail on the left side of the data. So if more than half the data is to the left of our peak. The distribution is then symmetrical only if the left and the right sides of the distribution, when split down the middle, are roughly mirror images of each other. So this bimodal distribution, the bell shape, the triangle, and the uniform all seem to be fairly symmetrical, but the other ones not so much. And that's okay. It's just a property to keep in mind. Another big, I mentioned bell shape, right? I should probably talk about the big distribution, the normal distribution. We'll be using this a lot in class. We won't be doing a lot of hardcore calculations, but it's usually playing in the background, doing a lot of the heavy lifting for us, especially when we go further down the road. It's often referred to as the bell curve because it looks like a bell or a mound-shaped curve. And it finds itself naturally representing a whole bunch of things in the real world, like heights and distribution of men in the USA. Looks fairly bell-shaped. One nice property is that it's pretty symmetrical and that about 95% of all values fall within 2 standard deviations from the mean. The mean plus or minus 2s, or 2 standard deviations. We'll use the bell curve indirectly when we go ahead and we prove our research results and we jump into statistical significance. But for right now, just sort of introduction of the bell curve, it's an important one. Now, normal distributions are fairly symmetrical. When it's symmetrical, the mean, the median, the mode should all be pretty much the same, especially if it's unimodal. If it's skewed, we might not have these things be all the same. And that's a hiccup. What kind of skewedness will we have? As I mentioned before, this tail, the reason why we have this tail is because we have some large observations here. We have a bunch of large observations. It's going to pull the mean in the direction of those large observations. And so if we have that, it's known as what's skewed to the right is also known as a positive skew. It skews the mean up, above the median. Symmetrical, they're the same, but if it's left skewed, this tails on the left side means we have some small values that are going to pull the mean down below the median and make it a negative skew. And we can compare these things through means and medians and not have to do the graph if we don't have it. So for example, comparing the mean to the median for the 2012 data on TV hours, is the distribution negatively skewed or positively skewed? In this case, it looks like the mean is 3.09, the median is 2. All right, you all. Is 3 bigger than 2? Yeah, of course it is. And yes, we have a positive skew. It means the mean is being pulled away from the center during the present of some higher values than typical. If we have these high values that are pulling this away, the mean might not be the best measure to talk about typical or center. If we have a lot of skewedness, you may prefer to talk about the median instead. The median is a good measure of center when it's symmetrical, but if not, the median might be a better way of doing about it. And in fact, that's why the 5-number summary is really nice, because no matter what, it doesn't matter what the observations might be in terms of skewedness, the median is pretty decent on picking up the 50% mark of the data. And if you have any decent sample size or different good size of your survey, at least 20, the quartiles, Q1, Q3, do a good job as well. So in this case, it seems what the average amount of TV was recorded to 3 hours a day. It's worth noting that half the respondents were watching 2 hours of TV or less. And it's important to share with the interested public or policymakers so they can make informed decisions, because you don't want to say one thing when the data is really saying something else. Now, if we want to measure these numerical quantitative variables, we can do so with a histogram. And histogram can take many values as a graph that shows how often those measurements fall in a particular range of numerical values and represent the shape of our data. These ranges are typically determined by software, but we can adjust with these little bars, the values that fit between these bars. This is known as a class interval. Don't worry about it. We're not going to focus on that here. I like having a couple terms here and there, but to feel like I'm still talking to you, very sophisticated stats, but we won't focus on it because we really just want to say, what is this kind of type of shape that's telling us? And here it looks like it's kind of lumped between 0 and 10, and it seems to be, we see this tail that's popping up, and it might be skewed to the right. But be careful. This data is indicated by, or is dictated by the class intervals a little bit. If I were to change these intervals, it might change the shape of the histogram, change the shape of the data, tell us a very different story. Histograms are great for visualizing the shape of data and whether it's skewed. We describe what the data appears to be lumped together, responds between 15 and 25, as well as 35 and 55 years old. Or we could have the responses between 10 hours and 0 hours. And while this is okay, it's not difficult to see how these things are lumped together. What might also aid and benefit this stuff is what's called a density plot. A density plot basically tries to take this histogram and shape it to look like a graph you might remember or even loathe from algebra class. But what's nice is that you can sort of see what areas, what ranges sort of hit the highest here and how things seems to sort of taper off when we get beyond 10 hours. In this class, we're going to go ahead and we're going to put them actually together. We take the density plot, we take the histogram, and we can actually use Jamovi to do both of them simultaneously and get what we're going to call a histogram density plot. And that gives us 2 graphs in one. Lots of information. We can also explore our data through what's known as box plots. And box plots basically are a way to help take our 5-number summary and visualize how the data breaks up based on it. The first thing we'd do, if we had to do this all by hand, is to draw a rectangular box that ends Q1 to Q3. The median of data is usually the line that splits the two. So book costs for introductory nursing students going from $300 to maybe over $800, $900 even. Oof. Textbooks are expensive, y'all. But from here, once you make this sort of rectangle, this box going from Q1 to Q3, it gives us a middle 50%. And then we take what we call whiskers, and they're drawn at the ends of the rectangle that extend either to the minimum, maximum, or if there happen to be values that are a little bit weird, ones that are called outliers. There's formulas out there that sort of represent how far data should extend to. And we'll take it to the value that's the most safe without feeling like it's too much of an oddball. These are called adjacent values. Don't have to worry about it too much. Jamovi will do the work, basically creating a top whisker and a bottom whisker. If there are any observations that extend beyond the whiskers, we'll consider them as possible outliers, and Jamovi will represent them with dots like so. Box plot can also help us determine whether there's skewedness. If the top whisker is noticeably larger than the bottom one, like here, or if the top rectangle is noticeably larger than the bottom rectangle, the data probably is going to be considered to be skewed to the right or positively skewed. On the flip side, if the top whisker is smaller than the bottom, or the top rectangle is smaller than the bottom, then it might be negatively skewed or skewed to the left. In this box plots here, you can see this is much larger than this one. So it's probably positively skewed to the right. It'll also provide us if there are suspected outliers. Basically, these are the values that might have unusual observations, and it's worthy to investigate further to make sure that things were answered correctly, just in case. Whew, it was a lot. Feel free to take a short break, pause it, take a breather, and take some time to review, test your knowledge, and we'll go on to the next piece kind of whenever you're ready. Skimming through. So leaning into descriptives. To be honest, that was the mathiest stuff we'll do for this module. So now how do I write up these results? That's the important part, right? That's part of your homework, part of the blog post. That's like 2/3 of your grade. So we want to make sure we write these things up nicely. So some writing tips become, so going through and we'll look at this data. We have the mean, standard deviation, usually will go hand in hand, median, and we'll have our minimum, maximum, and our quartiles. So first thing you do whenever you're writing this stuff up, do what you might do in a sociology class that doesn't involve data. Start with your topic sentence and explain it out a little further. So time spent watching TV can detract from other activities such as exercise, meaningful activities, and for that reason, it's important to monitor television time. And note, that statement kind of brings it as an introductory idea, comment, policy to the surface to analyze. Using GSS data from 2012, our findings suggest that half the respondents are watching about 2 hours of TV per day. And in parentheses, I use median equals 2, so it gives me a formal way to describe it, with an average of roughly 3 hours per day. So I have the mean, and I'll provide the standard deviation as well. While the middle half of respondents reported watching between 1 to 4 hours, so there's your Q1, Q3, there were reported instances of some people watching television for 24-hour periods at a time, which may be cause for concern. Direction to the future. Time in front of the TV is not only a measure of screen time these days, and other questions may need to be asked regarding time spent in front of the computer or one cell phone to get a better picture of time use in the sedentary lifestyle. And note, this directions for the future deals with the validity of the question and whether the measurements are actually done well. And that's your next goal once you deal with this stuff. Describing the histogram density plot, usually I say do 1 to 2 sentences. It doesn't have to be huge. Mention the shape and the skewedness as well as where the data appears to pile up. From our histogram density plots, we see the data appears to be skewed to the right, with most individuals watching between 1 or 10 or 0 to 10 hours. Also, the box plot also suggests that the data is positively skewed, and many respondents are outliers in terms of TV watching. You could describe the fact that, the case of people watching recording television 24/7, and that's what they're responding to, and dealing with the sort of question of validity from there. As a reminder, review the tips for writing research in this module and all others to follow. Carefully review the rules for reporting measures of central tendency, measures of dispersion, and graph visuals. You also use these tools in reporting on descriptive statistics on numeric data when writing up your findings to do well in your blog post and as well on your homework assignments. Same thing. And if you feel like this is going to be a lot, don't stress. The Jamovi short video that is also in this module is going to make stuff, I think, feel a little less hectic. Go through it, make sure everything makes sense, and you should be good to go. Take a short break. Everything after this is just quiz stuff, practice quiz stuff. Before going forward, feel free to test your knowledge, what you've learned so far, before you start the real quiz or the blog post or the homeworks. But meanwhile, take a deep breath. Let out a primal rage scream if you need to. You went through a lot. The modules get busy sometimes, and it's going to pick up, but I think you got this. It might feel new and terrifying, but remember our main goal in this class is to report on our data, not calculate things by hand. The formulas, that I'm a little bit horrible, diabolical, make you all see and experience. Those are just so you can see them, or that they are made available to you all, because you deserve to have them in your repertoire, but you don't have to use them, especially in this class. We're going to focus more on computer stuff because that's what modern statistical folks do. We don't do stuff by hand at this level. We run it through a sophisticated computer program with our code that we maybe done because we're fancy folks, and we get the results and we analyze that from there. You got this. All right. Make sure to do all the things: homework, blog, quiz, time management survey. And if you have questions, hit up the discussions board. All right. Take care, folks.